high-performing projects, strategies for the Northeast, specifically focused on Philadelphia area, but these are principles that can apply to many other regions, as I know we've had a lot of folks joining us from all over the US as we've switched to the digital platform over the last several months. So this tonight's session on high-performing projects ties into a lot of the things we've been talking about in the second half of our series, which kicked off in December of last year. So for those of you who might have joined us back in July, we had Kim Shen talking about demystifying energy modeling and talking a bit about, and we talked before about integrated design process. Back in August last month, we talked about the environmental design tools that we can use to help leverage early design decisions. And even though we won't be talking about tools, you are going to hear a lot about sort of the early phases of design and passive strategies that help us lower the overall energy intensity of our buildings. And this is going to key in quite nicely with the next couple of sessions that we have. So next month, we're going to be talking about net zero buildings. We're going to have 3 specific case studies that we're going to walk through next month, sort of a small, medium, and large scale project of how they got those to net zero buildings. And then in November, we're going to be coming back and talking about the collaborative process, best practices for working with building performance specialists like Kim Shen. So all these things sort of stitch together quite nicely to one another as companions to each. So for those of you that just joined, we're going to be going through the passive strategies, but if you would just sign in the chat. Give us your name and your email. If you'd like to get CES credit for tonight, you get 1.5 health, safety, welfare credits for this. If you didn't register through the Philadelphia AIA website and give your AIA number, you can also include that in the chat window. Okay. Try this. Get that out of my way. Okay. All right. Trying to clear out so I can see everything. Okay. All right. So we're going to start by talking very broadly about the possibilities early on in design. So as we kick off any project, we want to start first by understanding the context within which we're operating. And by that, I mean the climate that you're building within, and the site within which your building is going to be situated, and the effects that climate have on that building design, access to sun and wind, etc. All the sort of climatological information. One of the reference standards which are quite helpful in these early stages is a new one that came out back in 2018 from ASHRAE called Standard 209. This is a standard for energy simulation aided design. This gives designers minimum information that they need to collect for the building performance based upon climate variables. So it's a really good framework for interfacing and dialoguing with your building performance specialist. This is something that Kim Shen brought to our attention a couple of months ago. And so in early stages, and by that I mean this can be as early as your request for proposal when you're putting in a proposal to a potential client or potential project, or your conceptual design phase, or even early schematic design. Those early phases is when you have a lot of latitude to move the needle on performance and to affect your loads, your sensible loads for the building by early decision making on this, taking climate and site into consideration. And you do this through a variety of tools, looking at your historical weather information. But one of the other things we want to bring to your attention is that we also would want to be looking at future projections of how climate change is going to affect weather patterns in terms of intensity of temperature that impact your comfort range for the building, weather patterns, etc., to see how those things are going to be affected over the next 10, 20, 30 years. And there are resources out there which we will provide all this information to you afterwards. We've got a variety of resources that we've been collecting to share out with folks along with this presentation, which is being recorded and will be posted to Vimeo after today's session. So the climate information that we get, and these are climate files from the Department of Energy. One way in which we can begin to evaluate the climate information for our project is through a free tool from the University of California, Los Angeles, UCLA's Climate Consultant tool. So you download these climate files, these EPW files, and you begin to run some early just macro scale analysis of what the climate says relative to passive strategies. So this is the climate consultant tool. I'm using ASHRAE standard 55, which takes in consideration not just the climate considerations, but also clothing, activity levels, metabolic rates, etc., to define where one would feel comfortable within this particular climate zone. So you download these weather files from the Department of Energy, or Ladybug has a nice graphic interface via mapping to show you where the climate is and how to download those files. You plug that into this particular tool and walk through a series of panels that will then begin to show you what the climate information is embedded within this file, which is just an Excel file database of information. So what you see here on the screen is temperature in the upper left, wind velocity ranges, radiation available on site for photovoltaics, for example, or passive solar, and ground temperature. And these are broken down by months, going left to right, and minimum maximum ranges within these. So we take this climatological information for our area of Philadelphia, which is climate zone 4A. And before I go into the analysis of the information, it's going to be leveraging a tool which many of you may or may not remember from our undergraduate years of mechanical systems for architects, where we got familiar with something called the psychrometric chart. Mechanical engineers are probably much more versed with this as they deal with this daily. But you look at the psychrometric chart. Along the bottom is the temperature scale, and these curving lines that we see here, that I have one highlighted in red, is relative humidity. Maximum 100% saturation of relative humidity is at the upper end of this, and 0 is down here along the bottom with dry bulb. But what we're really going to be concerned with on a psychrometric chart is this general range that I've highlighted here in green, where if we had no other conditions to take into consideration, if it was just temperature and relative humidity, where would we feel comfortable? And so this is just showing sort of a bracketing of 20% to 80% relative humidity and 72% to 82, or 72 degrees to 82 degrees temperature range, a sort of thermal comfort zone. It's not quite that simple because there's a whole variety of body types, of clothing situations, of activity levels that are taken into consideration. But in Climate Consultant, you're running through these panels showing you the climate information, and the very last panel is a passive strategy, design strategy panel. And I have two versions of this highlighted here. This first one, all of these green and yellow lines are data points of maximum and minimum for every day. This is for shoulder season, or for the spring season, March through June. That shows temperature data for that time of the year in Philadelphia, how it ranges, and the blue zone here is your thermal comfort band. So everything outside of that is other strategies that can help you extend the thermal comfort zone for this climate. So here in brown is internal heat gain. So if I had glazing on the south that's capturing some of that free external sun radiation to the interior space, then I could expand my thermal comfort zone passively without having to engage active strategies, mechanical systems, to be comfortable within the interior space. Some other things are natural ventilation. We know that's challenging in Philadelphia, which is both a heating dominant and cooling dominant climate, but there are times of the year where you have opportunities to open the building, depending upon your use, to external free resources like wind. Versus here's a summertime condition where all the data that we have for maximum minimum for every day in the summertime, you see a lot of this starts to fall outside. It's just too humid and too warm, really, for passive, free energy strategies to extend the thermal comfort zone. But the light blue is where you've got some passive ventilation that helps with that. So mention these things because what we're going to be focused on today is talking through passive design strategies, things that help us to reduce our overall energy consumption for the building before we even begin to evaluate active strategies, the types of mechanical systems that we might employ in this. Those will be things that come later. We won't be addressing active systems tonight. We're really going to focus on the passive strategies and going through some of the fundamentals and specifics of how these things apply to other buildings. The passive strategies are theoretically and realistically much more economical to sort of capture those free passive energy opportunities early on in design. On this, sort of the building massing to wall assemblies is sort of least expensive. There are some things about building massing that have a cost associated to it, but generally speaking, things at the upper end of this are less expensive than those that are down at the end, especially when you get to the active side of things. And so, we have a lot of early design decisions that we'll be making about the massing of the building, where we place program within the building, the orientation, what the floor-to-floor heights and window-to-wall ratios. And we're going to go through each of these things laid out here in the design decisions and talk a little bit about how those things have an impact to the energy performance for the building. So with that, I'm going to pass it over to Brian Smiley to talk about building massing, program adjacencies, and building orientation. And again, if you just joined, please enter your name and your email into the chat. Thank you.
Okay, thank you, David. So as David mentioned, I'm going to be talking about massing initially. And obviously this is the first thing that folks look at when you're done with your benchmarking and early visioning, let's just say. So I like to say these very first steps about thinking about massing, it's very similar to a tuning orchestra, or think of it as like a jazz orchestra, a really good one. It may sound like a little bit of cacophony at first. All the instruments are playing, everybody's vying for attention at equal volume, and you're wondering what's going to come of this. Is something going to come to the top and play the first melody? Which instrument it's going to be? So let's go to the first slide here, David. So when you're looking at your massing, after you've first understood what your site constraints are, do you have an urban site? Is it hilly? Is there a lot of woods? Is there a water body somewhere? You may find that your orientation may be locked based off of those constraints. And also there might be height constraints too. There might be some community drivers as well, some essential features or an amenity that's worth celebrating. You might have some wetlands, woods, prevailing winds that you want to take advantage of, some amazing views, some form of experiential driver that's going to really drive your geometry. But on the flip side of that, when you're looking at low energy design, you really have to understand, do you have the opportunity to play? Can you shape the building on the site? Can you make it ready for really low energy design, net zero design? Can you make it ready for renewables? And, you know, the renewables may not drive your early investigations, especially if, you know, it may for a smaller building, and especially those on wooded sites. But for large buildings, renewables may not drive the orientation. But really what we want to do is start to investigate different forms very broadly and see what the impacts are on heating and cooling. You can see the bars on this diagram that show the different measurements for those factors. So ideally, these early investigations will be done with the help of an engineer. If you were on our earlier presentation with Kim Shin, one of our previous presenters, if you were an architect that tried to do all these investigations yourself, you very likely would get bopped on the forehead by Kim. But you know, that there are some things that you can do to lay the foundation. So next slide, David. So one of the things that architects can do in these early massing investigations is really look at the effect of daylighting on these different mass iterations and options. So, you know, you can see in this slide that you have a lot of different geometries, low, you know, a square bar, a tall bar, and doing that investigation, just thinking about the daylighting opportunities, and we'll talk a little bit more about that later, is something that architects can drive in this early stage. Next slide, David. This next slide talks a little bit about massing and somewhat orientation as well, but in the context of massing, if you were just to look at those two top schemes, the long bar versus the square, and compare the EUI measurements that you see here for different building types. This was a great investigation that Digsaw had done using Cove Tool, but you can see right off the bat in the middle for the square schemes, across the board, they're generally a lower EUI. And so that's very interesting, and you may wonder why, and of course there's more layers to that that I'll get into in a minute. So next slide. One important thing to talk about is the degree of modeling at which you should be doing at this stage. The image on the left is really just your broad geometry, and you can see that you can get into some intersect massing, but if you look at the diagrams at the bottom that's showing the solar heat gain for these various schemes, there's not a lot of difference when you start to put in that extra time and effort on the intersect modeling and geometry. So it's really not worthwhile at this point. And unless you have a constrained site and you're really pretty set on your massing, you should not be doing the detailed facade articulation over on the right at this stage. We'll be talking a little bit more about that, but that's the important message for this early stage modeling. And that's an important thing to mention here, because I'd like to say that all architects do their analysis and let that influence the design, but in reality, I would bet that a lot of people work at firms where the geometry is set by other factors, be it program or experiential, and the analysis folks are asked to, well, just run a model here and tell me how I'm doing. It would be much better to get to low energy design, to let the modeling influence the form a little bit, and then approach the owner with those value propositions in a way. Okay, next slide. So we're going to talk about programming adjacencies and how that can influence your model. The next slide, David. So this is a project that the TransSolar consulting group had done for a university client, where they really started to look at, TransSolar is an energy modeling and sustainability consulting company, and they have some really sophisticated tools to investigate energy. But one of the things they said on this project is that they really look at energy or program as blocks of energy, whereas as architects, we typically look at program as space. And that's important. You can see these early schemes where they started to look at this large block, this blue block that you see in those top diagrams, which were clean rooms. You know, how can we manage that large energy use? And in the diagram to the right, you see that there is a red line that's below grade. And the solution was to really push that high energy use to low grade. And, you know, the other elements wanted to be above grade and could absorb, you know, some degree of natural ventilation. So you see the diagram there looking at how the prevailing winds and the bar was oriented to take advantage of that. So, you know, again, there are some factors of the site that might influence your massing in addition to the energy. Of course, it's an iterative process, and we haven't really talked about this, as that diagram that we were seeing before showed, you know, for cost, low cost investigations at the top, and it gets more expensive to change building massing as you go on. But really letting these early decisions come along, you know, letting the energy dictate, so at the early stage. Next slide. This is about program, and this is an interesting concept that's really just starting to emerge. In the past few years, when I would ask an engineer, what if I put my offices on this side of the building, how would it change the energy model? I would almost never get a good answer. And at HOK, we're starting to look at Climate Studio by Solemna that really allows you to take program elements and analyze them in different areas of the building. And this is still in its early stages, so we still have a long way to go on this, but there's a few tools that Climate Studio has, adding something called air walls, where essentially, and you see in that top left diagram, you have your perimeter zone, and you identify that through an imaginary plane in the model, so you can start to play around with different program elements on that zone and how the systems might respond to that. And in the diagrams on the right, where you might have walls, you might have to introduce what's called adiabatic surfaces that are essentially surfaces, you can see the definition there, where no heat flow occurs between those, interior walls, ceilings, things like that, but can help define zones, essentially. And, you know, on the bar charts you see on the far right, you know, how is the heating and cooling affected, and equipment, where do you put those loads in your building? Next slide. So this is just another iteration of what you can look at with those perimeter zones. You know, this just uses a standard mechanical system, no economizer, but you can start to play around through percentages on the perimeter. On the bar chart, you may not be able to read that text, but different window to wall ratios. You know, do you have 30%, 40%, or less than 30%? What are the effects on lighting power density, your glazing types? You can start to input those, and your R values for your roof and wall, and what are your equipment loads? So you can start to, if you know those elements or those inputs at this early stage, you can start to input them. So next slide, David. So we're going to talk a little bit about building orientation, but before I do, I just want to touch upon a few questions. You know, at this point in the project, again, you're iterating a lot of different schemes. It's very hard to pause, but, you know, as I mentioned, that those zone systems use a very generic mechanical system. But at this point, you also want to be asking yourself, are there opportunities for natural ventilation? And even in this climate, it may be, in our shrinking shoulder seasons, it may be possible to integrate some degree of natural ventilation or a hybrid system or an economizer. You know, really, but you want to go to the owner with a couple of different schemes and value propositions to show why can the program be stacked as you show it, and will that result in significant energy? The next slide, David. So I want to share with you this slide, which shows different orientations and different massing of a project, a firehouse station that was done. And you can see in these different schemes, you have to, you may have different influences. Is energy, you know, the kBTU per square foot, the EUI, is that going to drive the scheme? Or the bottom option 3, the daylight autonomy, is that going to drive the scheme? And, you know, you can see there highlighted in green, it preferred, the lowest energy for that particular scheme, or rather that the daylight autonomy for that lowest scheme. And that's the one they ultimately went with because it had pretty good BTU. So these are all value propositions that you need to go to the owner with. Next slide. And at this stage, you're going to be also looking at going to your owner with, confirming where you're locating the program. And this is a study that we did that we were looking at, putting a laboratory bar on one side and an office on the other. So it's really just validation. And this is another opportunity for your energy model or your engineer to do another model to confirm your orientation and is it working, and they're going to get into the details as they're want to do and confirm the assumptions that you've made. All right, next slide. In this last slide, so we've talked a lot about broad moves, rotating the building around and changing its form. At this late stage in the game, you can really start to look at some of those intersecting geometries and see what are the opportunities for some massing articulation. And this is somewhat of a teaser of what we're going to be talking about in a few minutes about what are the benefits to daylighting when you tweak the geometry like what is shown here. Or can the geometry self-shade? Can you move program elements forward and back that can help the building shade itself? So with that, I'm going to pass it on to Jonathan, talk a little bit about window-wall ratio.
Yeah, thanks, Brian. So I'm going to talk a little bit about these three items: window-to-wall ratio, floor-to-floor heights, and window design. It sort of, as you get beyond the massing scale and you start to think a little bit more in detail, you're going to start looking at some of these elements individually. So you can go to the next slide, please. And the presentation today is really about what we're doing in this climate, mid-Atlantic climate, which for the time being is a blend of cooling and heating dominated loads. And so, for folks who are in heating dominated modes of design, they're going to have a different set of hierarchy. So if you're doing projects, either far north or far south, you may have a different set of priorities. But for this climate zone, we're now really in this, as we might say, the worst of both, right? We have to deal with hot and humid summers and cold and freezing winters. So you need to worry about all of those aspects. And what you do in terms of window to wall ratio will impact many of those things, right? You can see all of the items that are listed here specifically by season. And it's worth keeping in mind that you need to worry about both the energy impacts, which is a lot of the 2030 focus, as well as thermal comfort and potentials for natural ventilation as well. So we'll go to the next slide, please. This is the real part. I'm not sure what. Okay, thank you. This is the slide this is the slide to spend the longest on, the one people will be most excited about. But I'll just go briefly to say, the IBC has a maximum area of 30% window to wall ratio with a few exceptions based on certain types of other controls of 40%. And what that means is that in a given wall, 40% of the wall will be glazed and visible, and you'd be able to see through, and 60%, I'm not a mathematician, but 60% will be opaque. It's worth keeping in mind that as you do energy studies, 100% curtain wall with spandrel will perform differently than a wall that is punched openings in a solid wall, and we'll talk more about that later. But either way, this requirement is that your window to wall ratio is 40%. And you can see in the little area of the envelope calculations there, the reason I highlighted this is just to show that there is a difference in our climate zone 4A, that the southeast and west facades have a different requirement than the north facade, which is often another design challenge. Can you do a building that has different expression, and do you want it to look different, or do you want it to look the same? And what does that mean about us, that we want things to look the same that might be different? We'll go to the next slide, please. So it's worth keeping in mind. I think there's been for a long time a discussion where architects often think that to get good daylighting, you need 100% glazed walls. The maximum of 40 by code is intended to balance the effects of daylighting against the the impacts of extended heat gains and losses from having that much more window to wall ratio, limit glare, and all of these other items. Below 20% in some areas is really, you're not going to get as effective daylighting, but between 20 and 30% can be very effective, which is a lot less glass than many architects think that we need. And this is just on the left are just some graphics using a really simple tool called ComFen. There's a residential version called ResFen. It's put out by Lawrence Berkeley National Labs, so our tax dollars pay for it. And I can say even I was able to put these quick studies together very quickly. So this is a valuable tool for doing some quick analysis of what happens if you have, on the top line there, lots of glass, a middle amount of glass, less glass, and you can see very quickly, in this case, the daylight impacts. This tool also has energy impacts that pop out. It's really for a single zone, perimeter zone, and it gives you some relative comparisons. And the bottom three studies are the same percentage of glazing, but oriented in different ways to show one of them has a lot more glare at the perimeter, one of them has a lot more daylight penetration, and one of them is sort of in the middle. So it's, I think, a useful tool to say it's not just what the window to wall ratio is, but also where is it. You can go to the next slide, please. I think it's worth keeping in mind that part of what led a lot of the architectural community to overglaze buildings is a combination of different factors. That it was, it includes, the ones that really impact the performance, which are listed. What's the sill height? What's the head height? Are we doing continuous wall-to-wall glazing? Or is it individual lights of glass punched openings, which is, more of an aesthetic decision, but ends up having a big performance impact? It's worth noticing that, Brian's example of the residential model, they chose the scheme with smaller punched openings distributed throughout, which had much better daylighting because there was probably less overlighting and more appropriate levels of lighting. And of course, there's the challenge that doing a floor to ceiling, wall to wall glass for a lot of commercial applications is very attractive because it's unitizable, it's easily constructible, it's a single trade, it's off-site, it's all of those sorts of things. Not to mention our architectural obsession with the idea that all glass is, the higher the percentage of glass, the better the design is. So the thing to keep in mind with all of it, I think, is qualitatively for energy purposes, you're comparing yourself to a building with 40% glass. So if you build a building with 80% glass, it's going to be a big challenge. Kim Shin also mentioned that you're starting essentially, half a lap behind the rest of the runners in the race. If you're saying my glass, which even the best glass is much worse than the worst solid wall, needs to be as good if you've got 80% glazing. So we'll go to the next slide, please. And this is sort of a graphic that it goes along a little bit with some of the earlier massing studies and sort of orientation studies, but I think it's worth keeping in mind that even without modeling, a rule of thumb about how far daylight will penetrate into a building can be useful. So the diagram in the middle is a plan diagram of different plans of buildings, very simple buildings clearly, but it just shows that without doing any modeling, you can do a pretty quick offset from your building perimeter to see how far will the daylight generally get to, not counting exterior obstructions, and also how how much, how far will not only the daylight get to, but also what's the impact of that perimeter heat gains and losses. So it's worth keeping that in mind. And of course, knowing that that rule of thumb is based on window head height helps reinforce the idea that if the windows are higher on the wall you'll get more daylight penetration. If your floor-to-floor heights are higher, you'll have more possibility for penetration. But again, if your sill height is at the floor and your head height goes from 8 feet to 9 feet to 10 feet to 12 feet, your window-to-wall ratio will get higher. Next slide, please. So the last one is really just an image, an image from Pinterest, which is that, you know, I think a lot of, if you look around the city and look around architectural publications, there are a lot of buildings that are much higher glazing percentages, and I think the solution to that, the code is really limiting us in percentage, but there is a design solution that creative designers can find buildings that are both meeting the intent of expanses of glass where we want views and protection of opaque walls where we want protection. And it's really I see that as a challenge to the creativity of our design community. So on that, I'm going to turn it over to Josh, please, to go to the next.
Let me get unmuted there. Thanks, Jonathan. All right. David, if we go to the next slide. So picking up on what Jonathan was saying about talking about with windows, you know, I think there's a lot of there's some fundamentals that kind of underlie, you know, these decisions. So, you know, in addition to the window to wall area ratio, there's a lot we can do to mitigate the negative impacts of glazing and maximize the positives of glazing. Obviously, there's reasons we like a lot of windows. And so, you know, I think these diagrams on the right probably look pretty familiar to anybody who's been in an energy class in school. You know, obviously these are very simple representations: the horizontal shading devices, vertical fins, and then, you know, kind of combinations thereof, kind of an egg crate configuration. And while these are very simple, they're very effective. And then the key then is to implement the right strategies based on exposure. And, you know, we're going to simplify and just focus on the primary, directions, north, south, east, and west as a starting point. But the thing, you know, obviously we have modeling tools at our disposal that allow us to quickly get feedback on alternate exposures, and as well as other old solar geometry, sun angle calculators that some of us used to use. So, you know, obviously south in the northern hemisphere is a big consideration. And the south elevation is unique in that horizontal overhangs or louvers are really the right, the right strategy to reduce solar gain. On the east, west, and north exposures, you want to look at vertical and egg crate type of scenarios. And then aside from these, there's a lot of kind of more other familiar elements that can be implemented to the same effect. Porches, balconies, deeply recessed windows allow you to achieve some of the effects of fins and overhangs. And then of course, going back to what Jonathan was talking about, the goal here is to balance the shading strategies with the daylighting goals. You could go to the next slide. So just to do a quick review of solar geometry, I know we have a lot of tools now. Jonathan put up those ComFen studies, very quick, simple studies, and you can add shading devices to those same window studies that he did. So again, we're a mixed climate, as I think we've emphasized in a couple of our topics, our headings already. And so there's a sweet spot for how you want to size these shading devices. In the case of overhangs, of horizontal shading devices, you want to maximize your summer shading, and which also means minimizing your summer heat gain. In the winter, you're looking for a little more light, and you're looking for some of the warmth that the sun gives you. And so I think I did the calculation for Philadelphia, 40 degrees north latitude. The sun angle at noon on June 21st or on the summer solstice is 73.5 degrees above the horizon. In the winter, that same on December 21st, it's 26.5 degrees. So it's much different, two very different angles, as I think these diagrams show. And you can see this study below actually came from a project we did in our office, and I can show a picture of this building later, where we in fact put a parasol type element over the building that was designed for both summer shading and winter heat gain. And then when you get to the other elevations, north, east, and west, you want to look at vertical options, as you mentioned above. And the recommendation there is to turn the vertical fins at an angle towards the equator. Also, certainly don't hesitate to take advantage of trees on the east and west sides of the building. They can do a lot, and in particular, deciduous trees can be used in our climate to let light in the winter and provide shade in the summer. Next slide, David. So, there obviously we have lots of simulation tools at our disposal now, even for kind of single aspect, single location analysis and single exposure, et cetera. I thought these tables were interesting though. They're set up by latitude and by exposure, and it gets into many of the kind of the secondary exposures, northeast, southwest, etc. But as we mentioned earlier, shading devices can reduce the heat gain in windows by up to 80%. And this table actually tries to correlate shading coefficients with or shading factors, they call it, which based on the depth of horizontal overhangs versus the height of the window. So, for instance, if you were to look at a south elevation, the shading device, the same depth as the height of the window, would give you a shading coefficient of 0.46. And if you were to pull that overhang back to a quarter of the height of the window, you would still get a good bump in your shading coefficient of 0.23, and that's a pretty significant number. And so even a shallower overhang will provide some benefit to you. So I think those are some of the fundamentals of of shading devices, and I think we're going to move in next into, oh, sorry, one more. Thanks, David. Yeah, go ahead, go to the next slide. So, and again, so I showed you at the beginning the very simple, images of the overhang, the fins, the egg crate, but there's obviously, as designers, there's beautiful ways to do these things too, and very effective ways. I think, some of these images show fins, they show vegetation, they show very vernacular forms of shading, kind of homemade. I think the image on the upper right, is a quite a beautiful way to accomplish that egg crate type shading strategy that we were talking about, and in using the balconies to that effect. The image on the bottom towards the right actually is a project that we did a few years ago, where there was that parasol element that we were looking at in those daylighting sections, or in those sun angle sections, is used to shade that glass element underneath it. And then you can get into some very intricate lattice type louver or horizontal louver or vertical elements. So this just doesn't have to be just a kind of a slapped on type of thing. It can be very much integrated with the architecture. And I think from there we're going to segue into the wall assemblies.
Hey, thanks, Josh. So before we dig into wall assemblies a little bit more, I just want to pause on this diagram for a minute or a few seconds, just to reiterate that, that this is not, we know that this is not a linear process, that oftentimes you're balancing back and forth between these different investigations, but it's worth reiterating that by the time you start to do detailed shading analysis that Josh was just showing us, that you really don't want to be rethinking your building orientation, because as Josh said, the types of shading is going to affect, or it's going to respond to which orientation it's on. So what I'm going to talk about is wall assemblies, really getting to the nuts and bolts of your wall sandwich. The next slide. And some of what I'm going to talk about is really just good architecture, but it's not standard practice yet. And some of it goes a little bit beyond what we consider just good, code compliant design. So I have a few stream of consciousness points that I added up the top that talk about what I consider are important factors of good wall detailing, going beyond code. So when you're looking at a low energy building, high performance building, you really want to strive to avoid, if not eliminate, air leaks and uncontrolled heat. And a lot of the humidity that might come into your building also carries energy with it too. So it's something we need to be cognizant of. You can really do a great building that was oriented properly as a great shading, and you can undermine it by having a really leaky facade. And we'll talk a little bit about the execution of that. It's really key on how the contractor executes that plan, but it's not standard practice yet. And so obviously having a tight building means having a healthy building, not letting unintended pollution into the building, not having condensation and mold propagate, and the longevity of your facade and your structure is really dependent on that, not having deterioration from unintended condensation. So I have two diagrams at the bottom here, which are New York City requirements for the envelope of the building, and on the right is Canadian requirements, or what they call tightness plans, with a lot of factors that they have listed there that you need to address. So this is not code required in Philadelphia yet. I'm hopeful that this will become more standard practice, a lot of the things we're talking about, but even New York City and Canada don't have all the elements that I'm going to talk about that are really necessary to investigate if we're going to do net zero and low energy buildings. The next slide. Talking a little bit about just general wall assembly concepts. You have the mass wall system at the top, which we have a few diagrams there. There's the more historic type of wall assembly that we're used to seeing, really little or no insulation, just a thermal mass. And then in the middle are cavity or drainage system, drainage cavity, which also gets into rain screens. And then at the bottom is the sealed systems. And in the lower right hand, you see that you may not be able to read the text, I apologize there, but you have different exposure levels on the left of that diagram, going from high, medium to low. And high is where you might have a tall building with a stack effect, or high wind exposure on a hillside or some other exposed building. And when you get to the types of facades that are going from left to right, you have the face sealed on the left, and then on the right, you have the rain screens in that red diagram. And you have two different types of rain screens, but they really perform best in those higher exposure level environments. And you may say that even for medium rise or low rise buildings, that type of facade system would be more beneficial than your standard sealed systems, which are still used all around, be it for precast or an EIFS system or something of that nature. And you have two different types of rain screens. You have just a standard rain screen with a drainage cavity, and you have your compartmentalized or pressure equalized rain screen, which is really critical for tall buildings. So let's go to the next slide. Some of you may have heard of something called the perfect wall as well, So on the left, you have your standard bat insulation in the stud cavity. But as we know, and ASHRAE now recognizes that the studs, especially steel studs, have a thermal bridge associated with them and degrade the R value of that insulation significantly. And that can really wreak havoc with the dew point in your wall system, especially in the Northeast and Philadelphia area. So the perfect wall on the right is something that has emerged where you see different versions of this. Some of it retain the bat insulation in the stud cavity, but you know, personally and at a lot of the firms I've worked at over the past 15 years have really gone to this wall system where you have your outside cladding. You can read the wall assembly on the right there. You have your airspace, your drainage cavity, and then you have all your insulation is placed there. And you really want to think about the thermal bridging for your cladding support, which we'll talk about in a second. But then behind that, the blue line is your impermeable air vapor barrier, and you have no insulation. So let's go to the next slide. No insulation in the stud cavity. And one of the reasons for that, so you see the diagram on the right there, the therm diagram, where when you add that insulation into that stud cavity, you're moving your dew point into that insulation. And you have the potential in certain humidity and cold outside temperature environments to have condensation occur in your bat insulation, which I know is very often fiberglass, you know, and that doesn't do well with moisture, and your steel studs aren't going to do well either. So the diagram on the left is really saying put all your insulation outboard of your air and vapor barrier. Don't put anything in the stud cavity and ensure that you don't have any condensation there. And that seems very basic, and maybe some of you already know this, but I know a lot of people don't. So you know, there's other factors that you need to think about. And just go back one slide, such as NFPA 285. If you're familiar with the Grenfell Tower fire in London, you have to be cognizant of the amount of combustibles you put in your cavity as well, and pay attention to your window detailing. The next slide. So again, going beyond code, I'm not saying you have to, you know, go do passive house on every project, but hey, let's take some of those principles and try and incorporate them into all of our projects. And the ones I want to focus on here are continuous insulation, airtight construction, and minimizing the thermal bridging. And the other elements are important. We're just not going to talk about them today. So next slide. So one of the things that you see in the Canadian tightness plan requirements that I referenced earlier, and you see this in a lot of passive house projects, is to trace your insulation and air barrier or air and vapor barrier lines around your entire building. Do it in plan, do it in section, do it in more sections, do it in even more sections, and then you're going to get into the details. So next slide. And one of the first tasks that you need to do is determine, well, how much insulation do I need? And some of you may recall this slide from Kim Shim's presentation, where you have to find out what your code requirements are, but then really seek to exceed them if it's appropriate. And it's not always appropriate to exceed insulation values, because there are instances, like I'd mentioned, where adding too much insulation in your stud cavity can cause problems. But the idea is to do it thoughtfully and with building science behind you. And Kim has his formula here about trying to get the you know, the roof, the walls, and windows all working together for the right U value. So once you determine your insulation thicknesses, next slide, you'll want to trace this around your building, zooming into the details. And a few problem areas are always up at the parapet and at the foundation. So you really want to be thoughtful about how you detail those. And you know, some of this, again, is just good architecture. You need to avoid what we call rainmakers, you know, excessive condensation at the, you know, underside of your parapet there, where you have a lot of heat and humidity rising from your occupied space and hitting your curtain wall, your spandrel glass system there. And you know, just raining water under the right circumstances. So you have to be cognizant of that and avoid thermal bridges wherever you can. Next slide. So tracing this barrier through your window system is really critical. And, you know, at this point, you know, we've talked a lot about, you know, modeling different glazing systems. And, you know, you may have already started to study whether you have double or triple glass and where your perimeter radiation is, but you should be doing that in concert with this. But another aspect to this is you really want to align your window thermal break with your insulation. So you see that diagram on the right, just one way to do that. You know, but what that means is you're going to need to add sill support for your window. The window is now projecting over the cavity in the insulation, and you need some way to support that. And sometimes you might get into thermally breaking that support or thermally breaking your flashing, which is not typical construction at all. But it also means insetting your window. You're not putting your window way out by your brick. So you might have to add jamb extensions or return your brick. Think about how that's detailed. That can be tricky, but that's an important factor to look at here. Next slide. So we talked about thermal bridges. These are two proprietary products. I'm not going to mention what they are, but I hope they become more standard practice of ways to avoid continuous metal bridging through your facade to support your cladding. You have composite girts on the right there, which again help avoid thermal bridges. Next slide. And doing therm analysis where you have unique conditions. Designers love to have these offset glazing conditions. They're really problematic when it comes to your thermal breaks. This particular project had condensation forming, but it was avoided by adding some more insulation and, you know, extending that mullion into the building a little bit more. But, you know, it's really difficult to pull this off. As Jonathan said, you know, you're always going to do better with an opaque wall. You just can't get the same R value in this little mullion, this tiny little piece of insulation. You have to do all the insulation outboard of your mullion. If you put any insulation in that mullion, you say, oh yeah, I'm gonna put more insulation. You're gonna put condensation, the potential for your dew point in that mullion too, where it can't drain out. So that's a bad idea as well. Next slide. So this slide speaks for itself. Condensation forms on everything, and it creates the potential for mold to grow. And we don't want that. An owner doesn't want that. So next slide. There's a lot more pressure from contractors to do panelized construction, of course, unitized construction, windows everywhere. It's happening everywhere. So the chicken head, if you're familiar with unitized systems, whenever you use that, you need to test that system. But you know, given that there's more pressure for contractors to do this, they have to be cognizant that you can't just seal the system. So the diagram on the right is a panelized system where you might have a super joint, but you have movement there. But you have to reconcile your thermal insulation and your moisture management and your air and vapor barrier. And you can see there's sort of a pseudo chicken head in that particular proposal, but it's not as simple as contractors would have you believe. You really need to pay attention to this for low energy design. Next slide. So these last few slides just talk about contractor execution. This was from a Green Building United seminar on residential construction and some of the inspections that the city is now doing and some of the pitfalls that occur with standard construction practices. So these are things that, again, it's not in the current skill set of all contractors to be able to execute these buildings the way we need them to. Next slide. And this importance of contractor execution can be done on larger commercial buildings in a variety of ways. Of course, getting a building enclosure consultant on board is a really good idea, very early in design, so they can review your details and specs, but having them doing field testing is important. And a few critical things you can see there on the right. You're getting the contractors to buy in and understand that they're going to be testing, and you know, it's up to them to ensure that the tests go well. And you're going to do that by talking about it a lot, the scheduling of it, doing mock-ups, giving them checklists and, you know, getting them geared up and prepared to succeed on this project. And there's a whole bunch of tests that I won't go into there, but if you've ever done a project like that, it's my hope that this becomes a lot more standard practice. So with that, I think that's the last slide, and I'll pass it back over to David.
Unmute. All right, so Bunny, this is the point where we'll pass this over for you to run through the Q&A on this. Thanks to everybody who ran through all of the various passive strategies that help get us to our learning objectives for the day. So if anybody has any questions to our presenters, panelists, if you'll just pop that into the chat, and I'll let Bunny take it away.
Great, thanks, David, and thanks to all of our presenters. Marie, you had a question. Do you want to unmute yourself and ask it to the group? Sounds like we've already started to have a conversation about it, but I think it would be great for everyone to hear your question.
Yeah, sure. I guess I was just looking for...
Marie, we're having a little bit of trouble hearing you. Could you speak up a little louder or get closer to your mic?
Sure. Is this any better?
Yeah.
Okay. Yeah, I was just wondering if there are any recommendations for any of the passive strategies, or I guess semi-passive, which are the most effective on existing building renovation. Because obviously, you know, building massing, building orientation aren't very changeable. Program adjacencies might be, and so maybe I'm answering my own question here, but what are the best recommendations for how to approach this as passively as possible for an existing building?
Well,
thanks. Jonathan, do you want to kick this one off?
Yeah, I started to put some thoughts in the chat, and maybe it got a little bit too long. But I think some of the things, it's, you know, for some renovation projects, you do have the ability to affect the exterior wall from the inside. Although, as Brian pointed out, that can be really tricky if you're not careful. In some cases, you might be replacing windows, but in many cases for interior renovation, the exterior walls and the orientation and the window to wall ratio is all set. And then you have to work on what are the things you can control, which really brings you into the internal loads. Can you challenge the criteria for temperature and humidity set points? Can you challenge the criteria for lighting levels? And then the other thing, of course, to throw on the other side is, do we want to expand the amount of outdoor air ventilation and other kinds of things for health reasons, which, you know, move the energy in the other direction? But sometimes those kinds of challenges, you know, a lot of our clients anyway have lighting criteria that I think are conservative, and we can do things with lower light levels generally and task lighting and that sort of thing to reduce those interior demands.
Jonathan, just to pick up on that comment, and I think you know, we've seen the same thing on a lot of the existing building renovation projects that we do, and kind of one of our rules of thumb is to not change the performance of the existing wall. Oftentimes these are mass walls, and if you were to add, you know, warm side insulation, or you then run the risk of introducing moisture into that wall and kind of changing the dew point in that wall system. At times we've modeled some of these existing walls, and I think one of the most important strategies is to minimize infiltration, and that's often at the windows. And so oftentimes we've gone with minimal changes to the opaque walls, but upgrade the windows and you know, make sure those are sealed, or sometimes even leaving existing windows in place but sealing them better. You know, that's kind of another thing we've done on existing buildings.
yeah, I'd reiterate the piece about infiltration. You know, minimizing air movement through the envelope is sort of I think of it as always my first line of defense, because it's effectively an R value of 0 wherever you have air infiltrating through the envelope. If you're able to get into your team an energy building performance specialist, then, I would want to sort of start by evaluating how the building is performing, both thermally, energy code wise, daylighting. And, I've done, well, first I want to say that maintaining an existing building is great from just a carbon footprint perspective. If you can save an existing building and improve it for a new use, then you're going a long way towards trying to make the environment better overall. But I would challenge a little bit about accepting everything as sort of a given in this, that you may find that there's opportunities to change window to wall ratio if it makes sense. I think the point would be that first you sort of want to understand how the building's performing and evaluate for any and all opportunities. So if there's an opportunity to change the window to wall ratio because it makes sense from a variety of factors, programmatic, aesthetic, performatively, etc., then I would put all things on the table.
Okay, thank you.
We have a question from Kit about insulation. Kit, are you on the line to ask your
Yeah.
question?
Yeah. Hey, thanks for the presentation, everyone. So my question, I think, was kind of like polling, I guess, a little bit of the crowd, since we have a good number of people here, but maybe from a question directed towards the panelists is how often you are seeing firms adopting kind of the principles of the perfect wall. I think there's, in my experience, I'm seeing some leftover kind of thinking in terms of maybe early sustainability movements of just increasing the R value of walls by stuffing cavities full of insulation, not necessarily understanding where the dew point falls, and a bit of hesitancy to really adopt the concepts of the perfect wall with relying solely on continuous insulation. So I guess my question is, have you seen good case studies that maybe use both continuous outboard insulation and stud cavity and address the vapor issue? And maybe question number two is, do you suggest kind of moving to that perfect wall solution for, I mean, I guess it depends on the building type too, but I'll leave it open-ended.
I'll jump in on, sorry, were you going to start, David? Just to jump in on that one, I think the code actually now, just to clarify, does require continuous insulation. I think as of 2012, the codes have started doing that, although Pennsylvania skipped the 2012 cycle. And the same thing with continuous air vapor barrier, or I should say continuous vapor air barrier. And so, I think that is now required, and the code even says has some requirements. I doubt they're very often enforced, about showing details as to how that envelope is enclosed. But specific to your question, just as an example, I'm working on a project right now. We're actually doing a cavity wall system, and we have the 3 inches of continuous insulation in the cavity. But we did go ahead and added some insulation in the stud cavity, but we actually did some quick studies. We had it was an 8-inch deep cold form cavity. If we went up to 8 inches with that insulation, we were seeing the possibility of moisture inside the stud wall. And so we ended up, I think we backed off to 2.5, 3 inches. There's other reasons to put insulation in there. I mean, I think we actually put mineral wool in our stud cavities, and in part we're looking for the acoustic benefit to that. Was I think one of the thoughts there, but also the mineral wool would not deteriorate and moisture.
I think in addition to this, Kit, that how the wall is constructed is really important. So, you know, despite our best efforts to detail and to trace your air barrier and your insulative values around the building, the folks in the field constructing it, making sure that it's being built correctly is really important to that overall performance. And having, you know, done a building that was following LEED principles, but wasn't, you know, going through the LEED process, we had a facade commissioning agent on this to sort of help work with the team, both designer and contractor, to make sure that those things were meeting the performance criteria of the project. So I guess my point being is that we can do the best we can do on the detailing side, but the execution is really crucial.
Yeah, this is Brian. One thing I want to add too, I mean, I think it's obvious to most that the perfect wall is somewhat of a misnomer. That's why I put it in quotes on the presentation. You know, obviously you have to deal with a lot of factors, especially on existing construction. New construction, like I was showing, you can deal with a lot of those with the thermal bridging that happens in the wall and the cladding support. But to David's point, you know, there are a lot of passive house buildings that are dealing with this actively. And you know, the concept of putting a continuous air and vapor barrier in an existing building is very difficult, but possible. And there's a lot of concepts of, you know, it's much better to leave out the insulation because of the risks that involves, and also make the barriers more breathable, which is good, but not always. So I will say that existing buildings have a tall challenge. I don't have a quick and easy answer, and I wouldn't want to give one. So yeah, I'd be interested in hearing what other folks think as well.
Yeah, are there any additional comments from any of our audience members on either of these questions? Okay, then I'm going to turn it over. Oh, Sherman?
Yeah, Bonnie, I just wanted to add, I think some of that question depends too on the interior uses. If you have high humidity spaces or labs, hospitals, rooms that may be generating more moisture than a normal office or house up against the exterior wall, then it may become even a more critical factor about whether you put that insulation between the metal studs. Of course, addressing the thermal break issue of the metal studs has to be done no matter what, and that happens on how you connect that in outboard insulation and the cladding to the support. So that applies whether there's insulation between the studs or not. But yeah, it's a good question.
This is Brian again. One other thing I want to add is that during this time of COVID, we have some owners approaching us about adding humidity to existing buildings to deal with viral transmission and load, which, as you're probably thinking in the context of this discussion, can be really dangerous to increase that humidity level when the existing wall was not set up to do that.
All right. Go ahead, Laura.
I think some of this has to do with contract documents and insisting on air verification, and that the CA architect in the field must understand building science enough to understand how to look for and get that verification, and that the contractor or the contracts written in concert with the client need to include an air boss, or, you know, an air barrier czar, whatever you want to call them, that is responsible for checking and verifying that. This is a level of on-site stuff that Passive House requires, but that in general, it won't happen, and you won't know if it hasn't happened well without blower door testing and various other verification factors in order to know if you've accomplished the deed before you close things up, when it's easy to find and fix those things. relatively easy.
And I was gonna, this is Jonathan, I was gonna add, I mean, I was gonna jump in and tell everyone to read, Laura, your post in the chat, but thank you for saying it out loud. I was gonna add that for non-passive house buildings, we did have a presentation back in the old days when we had people coming into our office. There are some, you know, one of the challenges with commercial construction is a lot of times that sealant and air barrier is shared among multiple different contractors, whether it's the opaque wall contractor or the glazing contractor or, you know, the brick, you know, contractor or whatever, and they may be multiple different, but there are some examples of companies that basically do, you know, on a commercial scale, do sort of air barrier contractor that will warrant their air barrier work with all of the other groups, which is a level of detail that's really important, because that's the challenge is, you know, a not very well installed air barrier is not very, you know, not very helpful.
Right, right.
Pretty high, you know, pretty tough. Yeah.
Laura, you also had a comment in the chat about programming relationships,
About what?
about programming strategies and relationships.
Oh,
Can you share that
yeah.
with us?
I mean, it's been a number of years, but I can't remember the name of the architect in Europe, but they did. It's got to be 8 years ago. A whole thing on say you have a mixed use building that is you know, your typical commercial, office, and then residential at the top, and it's all about, you know, layers pancake wise. But instead of thinking it in terms of orientation, so that there might be a ground floor, you know, obviously residential retail or commercial retail space, but when you go up, instead it's orientation related. So the residential units, which can handle the sort of individual stuff of a southern exposure, as opposed to the internal heat gain dominated office spaces, which would be on the north side. So instead of thinking of it as a layer cake, you think of it as orientations and what kinds of programs. Additionally, say you have a church or an assembly or whatever that has large assembly spaces that don't require windows, then you would want to put those in, say, a heat dominated climate on the north side, so you don't have that heat loss through windows. And then you put communal spaces, lounges, you know, lobbies, etc., where you can control through shading on the southern side. So, you know, you know, that, you know, you didn't go into detail, but I, you know, trying to decipher the diagrams at the early part, but these are the least expensive and, you know, best ways to control a lot of those things. And some of them are some very simple factors that you just say, oh, you know, I've got my assembly space, we'll put it on this side or on that side. So just reiterating what looked like, which we couldn't drill down in some of those early diagrams that that were shown.
Yeah, that's great. That's a really nice compliment to some of the vertical examples that Brian was sharing, and also an opportunity in existing buildings, Marie. Not always an opportunity, maybe given some of the existing interior spaces, but potentially for reprogramming a space and thinking about it, even though it's sort of in that first category where maybe massing isn't as much of an option. Are there any final comments or questions from the group? All right, well, thank you all for joining us tonight. Oh, go ahead.
There's one from Mickey Chapa about dew point.
Mickey, do we have you on the line?
Oh, sorry, no audio, he says. Okay, so.
Mickey asks, if dew point analysis is not within your capacity or firm experience, is it possible to leverage certain product vendors to perform it for you for the main wall assemblies?
You know, actually, dew point is a pretty easy calculation to do. And it's really, you know, do you need 2 inches, 3 inches, you know, of insulation, and you know, that calculation is a fairly simple one that you can perform yourself to see if that insulation is just thick enough that that dew point is going to land where it needs to be in the insulation.
It doesn't require running a WUPI analysis?
I
Well,
mean,
if
it's
you're doing a
always
static,
better when a more complicated thing to do that, but your basic wall section
Mhm.
is not that difficult.
yeah, if you're doing just a static snapshot in
Right.
time for like your lowest, temperature, freezing point, or your hottest temperature, yeah, it's not as sophisticated as WUPI. It's not going to give you the factor of time, how the wall is performing over the course of the day or the week. But you can at least do a very simple static analysis of inside temperature, outside temperature, and U values of assemblies to figure out where your dew point will happen in a snapshot.
Right.
Right.
In a worst case scenario is what you want to grab.
Yeah.
Just like when you're doing that south facade, horizontal shading, you're
Mhm.
sort of capturing with a couple of, static conditions, your worst case scenario for
Mhm.
shading and letting sunlight in. Same thing with sort of your dew point as you're doing it based on a worst case scenario.
Right.
And obviously, if you can get a WUPI analysis, and they're not that expensive, in a big building, they're not that difficult to do. But in smaller projects, it might be a little more challenging in terms of cost. But it should just be common practice in a large project with a real budget.
Josh, do you have something to add?
Oh, I was just going to underscore what David was saying. I think in that same energy class I took in undergrad, we took the wall assembly and we did it by pencil and paper, and it was the delta T, the temperature differential between outside and inside, and there's ways to do that. And I see somebody else that actually had a comment on that too. I mean, it is a static calculation and not without its shortcomings.
And it's,
Yeah, it's an interesting question about whether or not a vendor would take that on, because you're dealing with so many different pieces that are coming together. Some window manufacturers and skylight manufacturers are doing daylight analysis now. It's sort of a cursory level, but I don't have any experience with a product vendor doing dew point analysis.
I would say, to just build upon, the comment about permeability that was raised here in the chat, or Chad Boardman's comment, is that if you reach out to the manufacturers and their technical departments, they will give you some guidance on these things. Like if having, build a building in Houston, or design a building in Houston, Texas versus Cambridge, Massachusetts, you've got different permeable factors that you want to take into consideration to make sure that the envelope is properly drying out. And you can have those conversations with the technical facilities with each of these manufacturers. So it's worthwhile reaching out to, air barrier manufacturers to talk these things through for your specific project.
And the most important place, I think, to do your to pay for a WUPI calculation outside your office would be in the junctions with windows and probably foundations. So I think it's well worth it if the project is of any scale that can afford it, and even smaller projects to do that. And WUPI, you can get a free version of WUPI, and they're not that difficult to run. But firms can do it, and some of them will do it for a couple $200-300 for a detail.
And for those who may not have been on one of the earlier presentations, there's a wonderful chart in the AIA's guide on building performance that shows the payback period for modeling. That in many instances, especially given buildings of a certain scale, that these energy modeling efforts pay back for themselves in a matter of months over the course of the lifespan of the building. So it's definitely a financial leverage point to be made on getting an energy performance specialist integrated to the team. And sometimes you can actually have these things supported and paid for by local utilities as well.
All right, we've got one more question. Want to know about the value of pressure equalized cladding or rain screen systems.
That is a good question.
Specifically, how to get the most value out of it for the cost.
Well, I guess one thing I would say about that is there are ways to do a cladding that is not particularly high tech, or you know, I think a lot of the rain screens are about the exterior material, which could be terracotta or something you know, more exotic along those lines. I think, you know, what's behind that is important, and the cladding material can be you know, is less significant in terms of its performance. I mean, it's meant to basically shield the wall. So I think that's you know, kind of one comment I would have. I've done a rain screen with you know, a metal panel, corrugated, or I should say, like a profile ribbed metal panel. You know, so not the most expensive cladding material you can imagine.
Well, I think there's a couple things embedded in that, or that's happening in this conversation. There's rain screen and there's pressure equalized rain screen. So you can simply have a rain screen which is open joint, you don't have caulk to those things, and it's just protecting your air barrier and your thermal envelope and allowing that cavity to just ventilate and keep moisture out of it. You can also try and create compartmentalization to the air cavity behind that, which is a pressure equalized air cavity. And having done that mostly with brick assemblies in different climates, you know, it's complicated, but it's not necessarily expensive. Having done this with, you know, in a rural area of North Carolina versus in the Northeast, it's just about proper detailing and sort of education to the contractor as to how this is meant to be installed, and walking them through. And this is the example where we had an envelope commissioning agent engaged on the project, but it was a very economical project overall. And what I would say with the pressure equalize, at least with doing this on masonry assemblies, is I never got a call back about efflorescence of like salt, you know, deposits on the face of the brick, which if you don't have, you know, pressure equalized, you know, if it's not properly installed and detailed, you're going to get moisture trapped in behind there, and it's going to make its way back out to the surface, and it's going to bring with that salt deposits, and you're going to get that call from the client as to like, what's going on with my building? It doesn't look like it's supposed to. So with the pressure equalized, it's you know, equalizing it so that air and moisture, rain, can't actually, you know, force its way back into the air cavity, because the outside air and the inside cavity equalizes between one another. And there's, I think, Bunny, you also put a link in the chat with a resource that sort of talks about that particular strategy.
Well, thank you all for joining us tonight. Thank you to our presenters for a really, really dense and fantastic presentation. If you're interested in being involved more with the COAT committee, our next monthly meeting is on Thursday at 8 a.m. We meet from 8 to 9 virtually, not at the Center for Architecture and Design. And we have 4 now, 5 committees with 1 focused on environmental justice. And on Thursday, we're going to have updates from each of our committees, and also a presentation on mass timber from a manufacturer that's doing prefabricated envelopes. And our next 2030 working group in October will be on October 12th. And we're going to be looking at 3 case studies of net zero projects, a small, a medium, and a large. And we hope you all can join us. Have a good night.
Thank you.